Part 3 of our week 1 learning guide for differential equations. We've covered a lot of problems and a lot of examples in the first 2 parts, and I'll be sure and link those below. That way you can access them if you miss them. I'll also put the link for the learning guide if you'd like to download it and have a copy and work right alongside of me. That would be great as well. If you are in my section of differential equations, then you'll note the coding that I'm using to help you know which example helps on which problem. So keep that in mind as you're working through the assignments for the class as well. Let's begin. This video is going to focus on initial value problems as well as growth and decay. Now we're going to look at the first problem. We have done something very similar to this when we were looking at part 1. We talked about separation of variables. We're going to use a similar approach here. We first of all need to isolate the dy dx. So let's do that. We'll do that by subtracting the 2xy to the other side. Now I'm going to get the dy dx off the denominator. Remember, my goal is to get all the x's on one side, all the y's on the other side, so that I can integrate. Next, I'm going to divide by y. And now I'm ready to integrate both sides. Now remember, think of that left side of the equation as 1 over y dy dx, because that's going to be, I'm sorry, 1 over y dy, because it's going to be a little bit easier to integrate. As the ln of the absolute value of y equals negative x squared plus c. Don't forget your constant of integration, because that is the reason you've been told the initial value. That's to help you find out what c is. So we're going to plug in 4 for x. We're going to plug in 1 for y. The ln of 1, of course, is 0. And so we get that our constant of integration is 16. So it turns out that my equation, my y, my solution becomes the ln of y equals negative x squared plus 16. Now we don't want to leave it like this. We want to try to solve for y most of the time. So I want you to remember that the base on the ln is e. And so we have e to this power equals y. And then think about when you add exponents, you were multiplying. So we can have y equals e to the negative x squared times e to the 16th. And if we want a number for e to the 16th, we definitely can put it in there. It is 8,886,110 and some change, of course, times e to the negative x squared there. So always try to solve for y if you can. If you can't, it's going to be okay later on in our course, but we want to try to if we can. Let's go ahead and take a look at number 2 then, the first of our word problems. I'm going to bring over another piece of paper simply because I'm probably going to run out of room and I want to make sure that I get everything involved for this problem. So notice in this problem, we're told that radioactive substances decay at a rate proportional to the amount, meaning that the derivative is equal to something times that amount that's left. So that's obviously what we're going to be starting with. K being some constant of proportionality, we'll probably have to find K. So we're told that a sample contains 4,000 atoms of a radioactive material. Given that it has a half-life of 700 million years, how long would it take to decay to 125 atoms? So we're going to begin by trying to solve for that equation that will relate the amount of the substance to time. So we're obviously going to separate our variables. Now remember, K is just a number. Keep that in mind. N and T are really the only variables we have here. We just don't know the value of K yet. So I've separated my variables. Now I'm ready to take the integral of both sides. So the integral of dn over n is the ln of the absolute value of n. And the Integral of k dt would be kt. Remember, k is a number. So the antiderivative of a number is a number times the variable. Now, we remember that ln has a base of e. So we'll go ahead and do e to the kt plus c equals n. I drop the absolute value because I know that e to some power is going to be positive. Remember that when we are adding exponents, we were originally multiplying the bases. And e to some number, e to a constant, is just a constant. All right. Now we need to figure out what k is, and we need to figure out what c is. Now, you were told a piece of information, two pieces that's important. It's told that the sample contains 4,000 atoms at the beginning, okay? So essentially, we are being given the point when t is 0, we have 4,000. So we'll use that to first of all solve. So I've got 4,000 equals c e to the k times 0. Now, k times 0 is 0. E to the 0 is 1. So essentially, I'm finding that c equals 4,000. And a lot of times, I won't say always, but a lot of times, the c that's in front here represents the initial amount. So my equation really becomes, oops, not y, let's use n. N equals 4,000 e to the kt. Now we need to use the second piece of information, which we were told it has a half-life of 700 million years. Well, let's let t represent millions of years. So that way we can use 700 instead of 700 million. So we're being told that when t is 700 million years, there's going to be half of the substance there. So we're being told that when t is 700, there's 2,000 atoms. This is going to help us find k. So let's put in 2,000 equals 4,000 e to the k times 700. And remember, t is representing millions of years. Now we need to solve for k. So we'll divide by a half. I'm sorry, we'll divide by 4,000, which will give us a half. And now to get that k out of the exponent, I'm going to have to take the ln of both sides. So I've got the ln of 1/2. It's the ln of e to the 700k. Now we know ln and e are inverses, so they cancel each other out. And I end up with k is 1 over 700 ln of a half. Now our equation is complete. We are simply going to substitute this in for n. So I've got that n is 4,000 e to the t times 1 over 700 ln of 1/2. Now we're ready to answer the question. We've done all of that work, and now we need to find out how long would it take for this to decay to 125 atoms? So now we're needing to know, well, what is T when N is 125? So let me make a little bit more room. I've got 125 equals 4,000 e to the t times 1 over 700 ln of a half. We're taking this equation and we're setting it equal to 1 over 25. So let's divide by 4,000. I know I can simplify that. I'm just probably going to wait till the end to simplify all of this because I'm going to have to take the ln of both sides. You can see that because I need to get that out of the exponent. When I do the ln of this side, of course, the ln and the e are going to cancel. And now I'm going to multiply by the 700. And then I'm going to divide by the ln of a half. So I've got 700 times the ln of 125 over 4,000 over the ln of a half. Now you can type all of that in your calculator, and I get T is 3,500. Remember, this is millions of years. So really, we're talking about 3 trillion, nope, 3,500,000,000 years to answer the question that was asked there. Okay, we've got one more in this section. Let's look at number 3. Oil is being pumped continuously from a certain oil well at a rate proportional to the amount of oil left. That is dy dt equals ky. We're told initially there is 1,000,000 gallons of oil in the well. 6 years later, 500,000. At what time will there be 50 gallons remaining? Again, I'm going to bring over another piece of paper simply so we have enough room to cover this problem in detail, get it all taken care of. Let's start with that differential equation, that dy dt. And I'm going to separate my variables just like we did before. If this seems like, wow, we've done this before, I'm glad that when we get to the point where problems tend to be like, oh, we've already done this the same way, then you start to know what you can expect, right? And that's a good place to be. Now, let's go ahead and integrate both sides. Now, we did a lot of these same steps in the previous problem, so I'm going to speed through this a little bit just because you've seen this to get to that point. Okay. Then remember, we were told the initial point was 1,000,000. If I can get the zeros in the right spot. So you can see why a lot of times we condense that down, makes it a little bit easier. So I've got 1,000,000 as my C. I'm going to stay here. I've got y equals 1,000,000. 3, 4, 5, 6 zeros. And now I've got to find k. Now remember, in our problem, we were told 6 years later there were 500,000. So we'll use 6 and 500,000 as our next point. We'll put 500,000 there. And we'll put a 6 in for t. Divide by your million will give you a half, e to the 6k. Now we take the ln of both sides. Again, I'm going a little bit fast because we did the same process in the previous problem. So now I'm going to divide by 6. I've got my k being 1/6 ln of a half. Now we'll take our equation, put our k in there. We've got 1,000,000 e to the t times 1/6 ln of a half. And then we need to answer the question now that we have the equation. When will there be 50,000 gallons left? So I'm going to put in 50,000 for my y here. And then I'm going to solve. Okay, so we'll do our 50,000 divided by 1,000,000. Let's see, that's going to cancel out 4 zeros. Got 5 over 100, which is 1/20th, equals e to the t times 1/6 ln of a half. We'll take the ln of both sides to get rid of the e on the right side. Now we can multiply by our 6 and divide by our ln of a half. Take a moment, put this in your calculator, and you should get t equals 25.932 years. So I hope this helps with the part 3 of the week 1 learning guide. If you have any questions or comments, please leave them in the comments below. I'd love the opportunity to clarify, explain a little bit more. Also, don't forget to hit the like and subscribe button. That way you get a notification every time a new video is posted. Bye for now.